The trace determinant plane. So in this lecture, we will look at the trace and determinant for linear systems. We'll look at the features of the trace determinant plane and talk a little bit about bifurcations of systems. So trace and determinant for linear systems, if we have a 2 by 2 matrix M, the trace is just the sum along the main diagonal, A plus D. So what's the trace of these two matrices? Trace of M1 is 3 plus 1, that's 4. We just add up those numbers. Trace of M2 is a 4 by 4 matrix, it's still a square matrix. So it's trace, we just add up the numbers along that. 1 plus 5 plus 2 minus 8, which is 0. So trace is easy to find. Why we're interested in this is that the characteristic equation for finding eigenvalues can be written in terms of trace and determinant. So what's the characteristic equation for this system? This is a system of differential equations. This is the matrix M. We take A minus lambda, C, D minus lambda, B. We want the determinant of that equals to 0. That's our characteristic equation. If we multiply that out, it's A minus lambda times D minus lambda minus BC equals 0, because we multiply this times this minus that times that. And if you multiply that out, that becomes lambda squared minus A lambda minus D lambda plus AD minus BC equals 0, or lambda squared minus A plus D lambda plus the quantity AD minus BC equals 0. This is the trace, A plus D, right, is the trace of this, and this is the determinant. So lambda squared minus trace of M times lambda plus determinant of M. So that's the characteristic equation. The actual eigenvalues depend only on the trace and the determinant. If you know those, you know what the eigenvalues are. To get the eigenvectors, you need to know exactly what the numbers are, A, B, C, D. So eigenvalues can be written then in terms of the trace and the determinant, because if this is your quadratic equation up here, then this is the solution, the quadratic formula. So the classification of a system depends only on the trace and determinant. So you can plot systems in the trace determinant plane. So here's my trace determinant plane. This is T for trace. T for trace, D for determinant. So M1 is 3151. Its trace is 4. Its determinant D is 3 minus 5, so minus 2. And we'll zoom out a little bit so I can see my matrices a little bit better. Good. So M1 can be plotted as the point 4 minus 2. 4t minus 2. So that point in the trace determinant plane represents the matrix M1. M2 has trace equal to minus 4 and determinant equal to 4 minus 3, which is 1. So minus 4, 1. This is M1. This is M2. And then M3 has trace equal to 0, determinant equal to minus 9 plus 10, which is 1. So there's M3. So you can plot things in the trace determinant plane. They tell you what the matrices are. They don't tell you what the eigenvectors are. So is this useful or not? It actually turns out to be very useful because we can classify regions of the trace determinant plane according to the behavior of the corresponding system. So, right, how points in the trace determinant plane correspond to behaviors of the system. So if our minus trace lambda plus d equals 0. There's our characteristic equation. That means our eigenvectors are t over 2 plus or minus the square root of t squared minus 4d over 2. So there's our eigenvalues. So what can we say about this? So if d is less than 0, right, the system has two real eigenvalues of opposite sign. Why is that? Well, if d is less than 0, that means t squared minus 4d is actually greater than t squared. Right? If d is negative, we're actually adding and subtracting a negative, which means we're adding something. So this is actually going to be a number that's bigger than t squared. What that means is that t squared minus 4d, the square root of that, is going to be greater than the absolute value of t. What does that mean? Well, if we look at our equation, we'll take t plus or minus t squared minus 4d inside the square root. But this number here is bigger in absolute value than that number. So if, say, t is positive, right? So if t is greater than 0, then t plus t squared minus 4d, since they're both positive, that'll definitely be greater than 0. But t minus t squared minus 4d, square root of that, that'll be less than 0, because this is the bigger number, and t minus that is less than 0. So if d is less than 0, you have two real eigenvalues with opposite sign. So if we go way down here to my trace determinant plane, that means anywhere here, this is trace axis, this is my determinant axis, everything down here, oh, I shouldn't do that. This area here, d less than 0, means two real eigenvalues, lambda 1 less than 0, less than lambda 2. So any system that's in the bottom half of the plane here, right, negative d coordinate that's down in below the t-axis, is a saddle. It looks more or less like this. So our matrix M1, back from example 2 or 3 up there, just by knowing that it's below the t-axis, we know that it's a saddle. It'll have one real and one negative eigenvalue. And we know what the behavior of that system is. We don't know exactly where the eigenvectors are, but we know what the behavior is. So what other possibilities can the quadratic equation have? So again, lambda equals t over 2 plus or minus t squared minus 4d all over 2. If d equals 0, this becomes t over 2 lambda equals plus or minus square root of t squared over 2 right? And so one of these will, t over 2 plus t over 2 will be t, but t over 2 minus t over 2 is going to be 0. So you'll actually have a 0 eigenvalue. So d equals 0, what is that on the plane? D equals 0 is this horizontal axis. So that's that. And along that line, if we're negative here, if we have a negative t value, we'll just have a negative eigenvalue. On this side, with positive t values, we get lambda 1 greater than 0, and lambda 2 is a 0 vector. And we know what that kind of system looks like. You have a line, and then you have a bunch of stuff running away from it in the other eigenvector value direction, a line of equilibria and stuff running away from it. And here you'd have a line of equilibria and stuff running into it. So if we're anywhere along this line, d equals 0, the t-axis, we know we have a 0 eigenvalue. Okay, d equals t squared over 4, you have a repeated eigenvalue. Well, again, d equals t squared over 4 means that 4d equals t squared, and that means t squared minus 4d equals 0. So lambda equals t over 2, because this whole part, that's all 0. So if t is negative, you get a repeated eigenvalue with a negative value, eigenvalue. If t is positive, you get a repeated eigenvalue with a positive value. So that's this curve, this parabola. D equals t squared over 4. And on the positive side, over here, we're going to have a repeated eigenvalue. So our, and a positive t, so our solutions are going to look like that. And over here, on this parabola, d equals t squared over 4. Over here, we just have lambda repeated, lambda greater than 0. And over here, anywhere on this part, we have lambda repeated and a negative lambda, because we've got a negative t there. And so here, our solutions will look like this as they come in. That's what repeated eigenvalues look like. Okay, so we've got, one more section to do. Suppose d is greater than 0 and t equals 0. Well, if t equals 0, lambda equals minus 4d square root over 2, right? Because these t's are equal to 0. And if d is positive, this becomes lambda equals 2i square root of d over 2 plus or minus, right? It's got a purely complex eigenvalue. And so this is t equals 0, that's the d-axis, the positive part of the d-axis. So along the positive part of the d-axis, what we see is that we have purely complex eigenvalues, and what we have there as our solutions is called a center. Everything just rotates around there. So that's great. That gives us 4 regions we still have to think about. This one, this one, this one, and this one. Notice that our system M3 here now, we know it's a center, right? Everything's going to go around because we've just plotted there, and it's on, it's got a trace of 0. So the M3 from above, is a center. So if d is greater than t squared over 4 and t is not equal to 0, the system has complex eigenvalues. So again, lambda is t over 2 plus or minus t squared minus 4d all over 2. If d is greater than t squared over 4, that means 4d is bigger than t squared, and that means t squared minus 4d is less than 0, right? So the square root is going to be complex. So my lambda will be t over 2 plus minus I times b. B is some number. It's what you get when you grind everything through there. But the sign of the real part depends on the sign of t, right? If t is positive, you're spiraling out. If t is negative, you're spiraling in. So if we're in this region, this is where in here, d is greater than t squared over 4. You have a spiral source. And our solution curves like that as you go out. In this area here, d is greater than t squared over 4, but t is negative, so you're actually spiraling in. How do we go about doing that? So this is a spiral sink. And then the last two regions of these on the left and the right. And if t squared is between 0 and if d is between t squared and 4, then t squared minus 4d is positive. But t squared minus 4d is square root of it is going to be less than t. So lambda equals t over 2 plus or minus t squared minus 4d over 2. Now this part here is less than this in absolute value. So if I take the two and add them together, I'll still get a positive thing. If I take the two and subtract them, since this is the smaller, I'll still get a positive thing. So if we have positive t's here, d less than t squared over 4, you have 2 lambda 1, 2 distinct eigenvalues, both positive. And so our solution curves look something like that. That's what a phase plane looks like. And over here with t negative, d less than t squared over 4, we have lambda 1 less than lambda 2 less than 0. And our phase plane, everything is going in to 0. And so we know that our system M2 from the previous example, just because we plotted it on the plane and we know that it's below the green parabola, we know that it's going to be a sink. Right? So these are sinks and these are sources. Great. So there's our picture of the trace determinant plane, and we can classify all of our, if you just know the trace and the determinant, you can classify what kind of behavior the system has. And this is I stole this from Wikipedia. This is a nice, better picture of it. Spirals, the determinant, actually this should be not t, but this should be trace is here, determinant is here, the delta is t squared minus 4d. So t squared minus 4d equals 0, that's your repeated root. T squared minus 4d is negative. This is the thing inside the square root, remember, is inside the parabola. That gives you your complex eigenvalues. T squared minus 4d is, delta is greater than 0. And you've got a negative t, you have various attracting things, and various, the t is positive, you have various sources. And everything below the t-axis, that's all saddles. And everything that's on this is a repeated root. So it's a picture of what the phase plane looks like. So bifurcations of systems. So suppose we have a system that depends on a parameter, and then can we identify how the behavior of the system changes by looking at how it reacts upon the trace determinant plane. So here's a system that's got a parameter a in it. And we want to know, as we change a, how does the system change, right? A is part of the matrix. It affects what the eigenvalues are going to be. So let us point out here that the trace is a plus 1/2. The determinant is 1/2 a plus 5/4. So this equation we can solve for a, and then we can plug that in for a into the determinant equation. And the determinant equals 1/2 t minus 1/4 plus 5/4, or finally d equals 1/2 t plus 1. Great. So trace determinant. Determinant is playing the role of y. Trace is playing the role of x. So this is a line of slope 1/2 that goes through the point 1. I'm not going to be able to draw this super well, but let's see how well we can do this. So there's our system. As a changes, right, the value changes. So if we set a equal to 0, that gives me t equals 1/2. D equals 5/4. Right? So if a equals 0, plugging that into these two equations gives me 1/2 5/4. So 1/2 5/4 right there. That's a equals 0. So when a equals 0, we have a sink, a spiral sink, because that's inside the parabola to the right of the vertical line. A equals 1, t is equal to 3/2, d is equal to 1/2 plus 5/4, which is 7/4. So 3/2, 7/4, there's a equals 1. Also a spiral sink. So as a increases, we're going from left up to right. Okay, so there's a nice parametric curve. So what can we determine about this? Well, it's a saddle here because that's a negative determinant. At this point, you have a 0 eigenvalue. This little part in between here, that'll be a sink. We'll have 2 negative eigenvalues. That point there is a repeated eigenvalue. The part from here to here, this part in here, this is a spiral sink. This point here is a center, because that's where you have a 0 eigenvalue, purely complex eigenvalue, sorry. This is all a spiral source. Not sink, but source. Another repeated eigenvalue. And then out here, we have a source. So as A changes, as we go up along this path, we'll start out with a saddle as our phase diagram, something like that. And then we'll get a 0 eigenvalue, which means we'll have something like this with a negative exponent, so it'll be coming in there. A sink. It will have behavior like this. Everything going in. Then a repeated eigenvalue will have a line, and stuff is still going in because we still have a negative t. Everything on the left is a sink of some sort. In here, we have a spiral sink, so that means we have something going in. And then we have a center, and that's neither going in nor out. So on this line where t equals 0, you're not going in or out. T less than 0 is all some types of sinks, right? As long as you're above the x-axis, above the t-axis. It's a saddle down here, but then you have a 0 eigenvalue with everything going in, a sink here, repeated eigenvalue with everything going in, in a spiral sink. And then you have a center here. This is a spiral source. Now everything is spiraling out. This is a repeated eigenvalue, but t is positive out here. So everything is going out like that. And then we have a source out here. And so that means we have two directions and everything goes, well, then we go down there, out like that, out like that, out like that. There we go. So what we're interested in is at what values of A does the system change behavior, right? And so our equations are t equals A plus 1/2 and D equals 1/2 A plus 5/4. So the first place we want to look at is where do we have the 0 eigenvalue? And that's at D equals 0. And so what does A have to be so that D equals 0? A is minus 5/2. So if you plug minus 5/2 in for A here, you get minus 5/4 plus 5/4. So from t equals minus infinity to t equals minus 5/4, we have saddles, and then we get a 0 eigenvalue. When do we get a repeated eigenvalue? That's when we hit the parabola, and the parabola is d equals 1/4 t squared. So to solve that, we're actually going to need to use this equation, d equals 1/2 t plus 1. So our curve is this, our parabola is that. To find out where they intersect, we set them equal to each other. 1/4 t squared equals 1/2 t plus 1. And then we can pull everything together. We'll multiply through by 4, and we'll get t squared minus 2t minus 4 equals 0. So multiply through by 4, and then pulled everything over to the left side. And then t equals negative b, which is 2, plus or minus square root of 2 squared, which is 4, minus 4ad, which is going to be plus 16, over 2. So t is 1 plus or minus the square root of 5. So the square root of 5 is a little bit bigger than 2. So there's two values for t. One is this point. That's the negative value for t. That gives us this repeated eigenvalue. And the other one is here. That gives us the other repeated eigenvalue. So when a equals 1/2 plus square root of 5, that's when we're at this point. And when t equals 1 minus square root of 5, that tells me that a must be, right? If we know what t is, we can figure out what a is. 1/2 minus square root of 5, and that gives you this point. Great. And the last transition is where we have the center. And that's where t equals 0 or a equals minus 1/2. So what can we say about this then? from minus infinity to the 0 eigenvalue, which is minus 1/2, minus 5/2 is a saddle. So our system all the way up to here is a saddle. At a equals minus 5/2, we have a 0 eigenvalue and a negative eigenvalue. And then for a from minus 5/2 up to this point, right? And that's this value of a. We have a sink. And then at a equals 1/2 minus square root of 5, we have a double negative eigenvalue. And then from 1 minus square root of 5 to minus 1/2, we have a spiral sink. And then from a equals minus 1/2, that's where we have the center. When a is from minus 1/2 to 1 plus square root of 5, we have our spiral source. And then finally we go out, when a equals 1 plus square root of 5, we have repeated or double positive, that's a plus eigenvalue. And then finally, for any a bigger than 1 plus square root of 5, we have a source. Oh, there's still one more to go. So we've traced our system, saddle, to 0 eigenvalue, to sink, to repeated eigenvalue, to spiral sink, to center, to spiral source, to repeated eigenvalue, to source. And notice that the special cases, the 0 eigenvalue, the repeated eigenvalue, the center, the repeated eigenvalue, only occur for one point, one value of a. They're borderline cases. Between a spiral source and a source, you get a repeated eigenvalue. Between a saddle and a sink, you get a 0 eigenvalue. And here's one that we have seen before. Suppose a spring is spring constant 9, and a 1 unit mass is attached to the spring and a variable resistance is applied. Write the initial value problem for this differential equation, expresses an ODE, and how does the behavior of the system change as the resistance changes? So here's my trace, here's my determinant. Spring is spring constant 9 with a 1 unit mass and a variable friction. So initial conditions, y0, y1, this is your initial velocity, initial position, this is the spring equation. So if we set v, your velocity, equal to dy dt, then dv dt is equal to d squared y dt squared. We just differentiate both sides of this. And that's going to be equal to minus b dy dt minus 9y. And let me just add something here, b equals friction. And it's a parameter that just has to be greater than or equal to 0. So can we rewrite this as a system of equations? Sure, dy dt, dv dt equals some matrix times y and v. So dy dt equals v, so that must mean we have a 0 and 1 here. 0 times y plus 1 times v equals dy dt, that works. Minus 9y, and then minus b dy dt. right? So minus 9y minus bv. Great. So trace is minus b, and determinant is 0 is 9. So we want to graph this curve. It's got a constant determinant of 9, and t just depends on whatever your parameter is. Right? Whatever our friction is, we get minus t for that. So, oh, 9 is way off of that chart. I should have put in a different thing. So we'll say, we'll change our numbers here to be 2, 4, 8, 10, 12, and then this would be 9 would be in here somewhere. And so as b increases, we get different values of t. And what do we have here? The center, when we're doing springs, we call that an undamped spring. In here, this is t equals minus b. This was a spiral source, spiral sink. When we're dealing with springs, we called that an underdamped spring. Right at that point, that is double eigenvalue. And we called that critically damped. And remember that our solutions ended up having that extra t value in there somewhere. We had to multiply by t. And then out here we have a sink. And before we called that overdamped. Right? And if we're allowed to pump energy into the system, right, which would correspond to a positive b, then we get stuff out to the right. So systems can depend on parameters. Knowing the behavior of a system, you just track the system through the trace determinant plane, and you can see what kind of behaviors that you actually get out of it.